Ever wondered how chemists determine the concentration of an unknown acid or base in a solution? It's all about the magic of titration. Titration is a marvelous technique used in chemistry to measure the unknown concentration of a chemical entity. It's like a perfectly choreographed dance between two solutions, an acid and a base. This dance is what we call acid-base titration. It's a cornerstone in chemical analysis, offering a precise way to find out just how much acid or base exists in a particular solution. Let's picture it as a balancing act on a tightrope, where the acid and base strive to maintain equilibrium. And guess what? There are different types of this dance, each with its own unique steps and rhythm. We'll be exploring strong acid-strong base titration, weak acid-strong base titration, and even the titration of polyfunctional acids and bases. Ready to dive into the fascinating world of titration? Buckle up. Before we delve deeper, let's get a grasp on a couple of fundamental concepts: acid-base equilibria and the pH scale. Now imagine a world where water is the stage and acids and bases are the actors. In this world, acids and bases constantly interact, donating and accepting protons, creating a dynamic equilibrium. This interaction between acids and bases in water is what we call acid-base equilibria. Quite fascinating, isn't it? Now, onto the pH scale. Picture a scale running from 0 to 14. This, my friends, is the pH scale, a measure of how acidic or basic a solution is. The lower the pH, the more acidic the solution, and the higher the pH, the more basic or alkaline it is. A pH of 7 is considered neutral, like pure water. The pH scale isn't just random numbers, though. It's a logarithmic scale based on powers of 10. This means that each unit represents a 10-fold change in acidity or basicity. So a solution with a pH of 6 is 10 times more acidic than one with a pH of 7. In essence, the pH scale allows us to quantify the acidity or basicity of a solution, providing a vital tool for chemists and scientists alike. With a good understanding of pH, we're now equipped to tackle more complex topics. Ever wondered how acid and base species distribute themselves in relation to pH? Let's explore. Picture pH as a sliding scale, with each point representing a different balance of acid and base species. When the pH is low, we're in an acidic environment. Here, acidic species like hydronium ions, H3O+, dominate. As we slide up the pH scale into neutral territory around 7, both acidic and basic species are present, but neither dominates. Now let's slide further up the scale into the basic or alkaline end. Here, base species like hydroxide ions, OH, take the lead. This distribution isn't static, though. Adding acids or bases can shift the pH, altering the balance of species present. So the pH of a solution is more than just a number. It's a snapshot of the acid-base balance at that moment. The pH of a solution can drastically change the distribution of acid-base species. Not all acids and bases are created equal. Some are stronger than others, and some are, well, weak. Let's delve into these wallflowers of the acid-base world. Weak acids and bases may not be as assertive as their strong counterparts, but they have a unique set of properties that make them rather fascinating. To start, weak acids only partially ionize in water. This means they don't donate all their hydrogen ions to the solution. Instead, they hold back, leading to a more moderate pH level. Examples of weak acids include acetic acid and carbonic acid, the stuff that gives your soda its fizz. On the other hand, weak bases also partially ionize, but instead of donating hydrogen ions, they accept them. Ammonia, for instance, is a classic example of a weak base. Now that we've touched on weak acids and bases, let's bring in the salts. Salts of weak acids and bases are the products of their reaction with a strong base or acid, respectively. Take sodium acetate, for example. It's a salt that's formed when acetic acid, a weak acid, reacts with sodium hydroxide, a strong base. Now, here's the interesting part. These salts can also affect the pH of a solution. How, you ask? Well, when dissolved in water, they can produce ions that interact with water molecules to either produce or consume hydrogen ions, thereby affecting the solution's acidity or alkalinity. Remember, the strength of an acid or base doesn't necessarily equate to its danger or usefulness. Weak acids and bases and their salts play crucial roles in chemistry and in our daily lives. They're in the food we eat, the medicines we take, and even the air we breathe. So, Next time you hear the term weak associated with an acid or a base, don't underestimate it. These characters may be weak in terms of ionization, but they certainly pack a punch in the grand scheme of things. The strength of an acid or base can greatly influence its behavior and interactions. Scene script. Buffers and polyprotic acids play a crucial role in maintaining stable pH levels. Let's find out how. Starting with buffers, these are solutions that resist changes in pH when small amounts of acid or base are added. They're like the peacekeepers of the chemistry world. Buffers are composed of a weak acid and its conjugate base, or a weak base and its conjugate acid. When an acid is added to a buffer, it's neutralized by the base component. And when a base is added, it's neutralized by the acid component. This delicate dance keeps the pH of the solution stable. Now let's talk about polyprotic acids. These are acids that can donate more than one proton per molecule in different steps. Common examples include sulfuric acid and phosphoric acid. Each proton donation corresponds to a unique Ka value, or acid dissociation constant, which measures the strength of the acid in solution. Polyprotic acids also form salts, which are important in many chemical reactions. Polyprotic acids and their salts are fascinating because they can participate in multiple acid-base reactions, each with a different Ka value. This multi-step process adds a layer of complexity to acid-base chemistry. So, why are buffers and polyprotic acids important? Well, they're everywhere. They're in our blood, our food, our oceans, and even in the air we breathe. They help maintain the pH balance necessary for life and many chemical processes. Buffers and polyprotic acids help keep our world in balance, chemically speaking. Now, back to titration. How can we visualize this process? Enter titration curves and indicators. Titration curves are graphical representations of a titration process. They plot the pH of the solution being titrated against the volume of the titrant added. Fascinating, isn't it? Let's delve a bit deeper. There are primarily 4 types of titration curves. First, we have the strong acid-strong base titration curve. This curve is characterized by a sharp vertical rise in the middle, indicating the neutralization point where both acid and base neutralize each other. Next, there's the weak acid-strong base titration curve. This one's a bit different. It has a more gradual slope because the weak acid doesn't fully ionize, and there's a buffer region where the pH changes minimally. On the flip side, we have the strong acid-weak base titration curve. Similar to the previous one, there's a buffer region, but the curve is inverted because we're adding acid to a base. Lastly, we have titration curves for polyfunctional acids and bases. These are a bit more complex because they have multiple vertical sections, each representing a different ionization step. Now imagine trying to spot the exact moment when an acid or base is neutralized, just by looking at a solution. Sounds tricky, right? That's where our handy helpers, the acid-base indicators, come into play. Indicators are substances that change color at different pH levels. They allow us to visually spot when our solution hits the neutralization point. There are several indicators we could use, each with its unique pH range. Some common ones include litmus, phenolphthalein, and bromoethyl blue. In the grand scheme of titration, these indicators help us find out the exact volume of titrant needed to neutralize the solution. This, in turn, lets us determine the concentration of the unknown solution. With a titration curve and a good indicator, we can accurately determine the concentration of an unknown solution. We've covered a lot today, from the basics of titration to the complexities of acid-base equilibria and pH. We started our journey with acid-base titration theories, diving into the intricacies of how acids and bases react in a controlled environment. We then explored the fascinating world of acid-base equilibria and the pH scale, understanding how these concepts govern the behavior of acids and bases in water. We also touched on the distribution of acid-base species with pH and how weak acids and bases, as well as their salts, play a crucial role in this distribution. Our journey took us deeper into the realm of buffers and polyprotic acids, key players in maintaining pH stability. Lastly, we delved into the captivating visuals of titration curves and the role of indicators in acid-base titrations. With these concepts under your belt, you're well on your way to mastering the world of acid-base chemistry. Remember to subscribe for more because you won't find me later.